Okay, so we're looking for the number C for which the derivative at that point is equal to the slope of the line through the two endpoints. So let's see. The derivative is just minus sine of x minus cosine of x. We're going to put in a C there. Minus sine of C minus cosine of C. F of B will be f of 2 pi. So it's going to be cosine of 2 pi minus the sine of 2 pi. And then f of A is cosine of 0 minus the sine of 0. And then on the bottom, 2 pi minus 0. Is that the way you started it? Yes. But the sine of 2 pi and the sine of 0 are both 0. Cosine of 2 pi and the cosine of 0 are both 1. So I have 1 minus 0 minus 1 minus 0. So I get 0 on top, right? So we're solving the equation minus sine of C minus cosine of C is equal to 0. Or you can say that's where minus sine of C is equal to the positive cosine. Do you know where the sine and cosine are equal? They're equal at pi over 4, so they're going to be opposite in sign in quadrant 2 and in quadrant 4, right? So we're looking, our reference angle is pi over 4. But they are opposite in sign in quadrant 2 and in quadrant 4. So which multiple of pi over 4 is in quadrant 2? 3 pi over 4. And now in quadrant 4, 5 pi over 4. So there are two values in this case. No, that's quadrant 3. I'm sorry. Yes. A little bit more. 7 pi over 4. 7 pi over 4. 7 pi over 4 is in quadrant 4. Not quite 2 pi. 2 pi is 8 pi over 4. So that's, you'd have to really mess with the trig in order to get an angle over here that you would know. Otherwise, you would just write your answer in terms of an inverse trig function. And so I had to find some place where my numerator was 0. And I think that's one of your, a version of your, that's what I might have thrown a minus sign in here where my work didn't have it. Okay. Okay, so what we're going to do in section 4.3 is we're going to open up our intervals. On section 4.1, we had closed intervals, and we're looking for the absolute largest y value in that closed interval and the absolute smallest y value in that closed interval. Now we're going to be interested more in where the graph has its turns and its little peaks and valleys. And the peaks are going to be called relative extreme values, and the valleys down at the bottom will be called a relative minimum, because they're relative to the points just around them. So let's rub that off. Everything about the shape of a graph, almost everything, can be determined by looking at the derivatives, the first and the second derivative of a function. So section 4.3. What the derivatives tell us about the graph of a function. Let's just draw some function here. That marker. Something like that. And I'll put the x-axis down here. Ooh, that's a crooked old x-axis. Notice that I've got a nice continuous function over that interval. And it has a peak right here, bottoms out here, another little mini peak here, a little sharp corner there. Those are the points that we classify as critical numbers. Remember from the other section? So I'm going to label them as C1, C2, C3, and C4. So notice that this function f is a continuous function with critical numbers at x is C1, C2, C3, C4. And what makes something a critical number for a continuous function is that it's a place where the derivative is 0 or where the derivative fails to exist. So if I drew the tangent line right here, let's say f prime here is 0, same deal here and here. Where there's a sharp corner, we don't really have a tangent line. So we'll just write that f prime does not exist here. Now I'm going to draw some tangent lines elsewhere on the graph. Over here, all of my tangent lines are going to follow the shape of the graph. They're all going to lean upward as I read from right to left. When I take the derivative and use those values of x in the derivative, I'm going to get positive numbers because those tangent lines have positive slope. And then if I continue to follow the graph where it's dropping here, all of those tangent lines are going to have negative slope. And same thing here, back up, positive slope, negative slope, and then positive slope. If I didn't know what the graph looked like, but I was able to take the derivative and I could find where it changes sign and where the graph, where the derivative is positive and where the derivative was negative, I could do all that stuff. Then I could fit the graph in under the tangent lines. And that's what we're going to do. The parts of the graph where the derivative is positive will all be rising like that. So we're going to call those parts increasing. And where the derivative is negative, the graph drops like a line with negative slope. So on those intervals, the function will be decreasing. So intervals on which, let's see, this next one's better than this one. This one I didn't like at all. That's the way I clean the house. Intervals on which, oh, that's not any better. F prime is positive has have the property that the graph is increasing. Indicate that the function f is increasing or rising as you read from left to right. Intervals on which f prime is negative indicate f is decreasing. And so those critical numbers where the graph changes from increasing to decreasing, those critical numbers will be called relative maximums. And the intervals in which the graph changes from decreasing to increasing will be called relative minimums. So in our picture, we have a relative max here. And here, because they're taller than the y values just around them. And then this one here is a relative min. And so is this sharp corner. So that picture tells us something called the first derivative test for relative extrema. Move my thingy over, way over this way. Yes, I'll write it right there. So first, oh, nice one. Derivative. Oops. Test. Relative extrema. Extrema is just the broad phrase about relative max or relative min. It's an extreme value. So when we go hunting for these relative extreme values, we take the derivative and find where the derivative is 0 or where the derivative fails to exist. Those are the critical numbers. Let x is equal to c be a critical number of f of x. In other words, f prime at c is equal to 0, or f prime at c does not exist. We're going to look at the sign of the derivative in intervals around the critical number. So I'm going to find my critical numbers, I'm going to put them on a number line, and I'm going to look at the sign of f prime. If I take a test point and plug it into the derivative and get something that's positive here and then negative here, that tells me the direction of the graph. Positive slope means it rises. Negative slope means it falls. And so if you have that situation, f of c is a relative maximum. So if you have that, then f of c is a relative max. If it goes the other way, you have a relative min. Let me see if I can squeeze it down here. If, when I put my critical number here, my sign of f prime, what's that, goes negative to positive, then the direction of the graph goes down followed by up. And so if you have that, then f of c is a relative min. So the y value is what is the max or the min, and the critical number just is the location of the max or min. So let's look for that first with an example, and then I'll add to this discussion what the second derivative tells us about the graph. So we're going to start with the function and know very little about what its graph looks like, but we'll look at the change in the sign of the derivative, and it tells us almost everything, what the graph looks like. So let's just start with a kind of easy polynomial function. maybe a third degree polynomial. If I give you a third degree polynomial, can you picture what the graph looks like? In general, what do they look like? They look like up, down, up. Unless I've got a change in sign, then it might go down, up, down, or something like that. So let's find a third degree polynomial here. Let's look at 4t cubed minus 12t squared plus 5. So I've got a t to the third power graph with a positive coefficient in front of the t cubed. So from what you know about from your pre-calculus class, it's going to go up, hit a relative max, come down, hit a relative min, and then keep going up like a little snake. So the steps are going to be these. Find all the critical numbers. Take the derivative, set it equal to 0, and see how many critical numbers you get. From our knowledge of a third degree polynomial, we should get 2 critical numbers. So take the derivative, see if you can factor that, and tell me what the 2 critical numbers are. If t is 0 and t is 2. Okay. So first, find all critical numbers. F prime looks like 12t squared minus 24t. I'm going to set that equal to 0. And as I do that, I'm going to pull out my common factor of 12t. My other factor is t minus 2. And I'll set each factor equal to 0 and solve for t. And I get t is equal to 0 and t is equal to 2. Now I'm going to make a number line, put those in order on the number line. So second, we're going to analyze the sign of f prime. Is that the way you spell analyze? Looks funny. There's t is 0. There's t is 2. You can use this version, but I'm going to use the factored version. F prime is equal to 12t times t minus 2. Because then I don't have to hold the number in my head. I can just hold the sign of the number in my head. Pick a number from each interval and plug it in. Whatever it does at that number, it does everywhere in that interval. Like here, if I put -1 in for t, that gives me a negative factor here, a negative factor there. Negative times negative is positive. If I put a 1 in for t, my first factor is positive, my second factor is negative. That means my product is negative. And then when I put 2 in for t, we can't put 2, let's put 3 in. Both factors are positive. So those are the slopes. That tells us the direction of f. Follow the slope. Positive slope leans this way, and then negative slope leans that way. And so we can kind of see what's going to happen at the critical number. It goes from rising to falling, which means I should have a relative max here, a relative min there. So by the first derivative test, we have a relative max at x is 0, relative min at x is 2. Let's write that as intervals, that it increases on the interval to the left of 0. So from minus infinity to 0. And then again to the right of 2. So I'll write that as from 2 to infinity. And then it decreases between 0 and 2. We're going to go ahead and graph this. So let's get the y values that go with each critical number. So now I'm going to go plug that back into the original function. F of 0 is 4 times 0 minus 12 times 0 plus 5. F of 2 is 4 times 8 minus 12 times 4 plus 5. So let's see, 4 times 8 is 32. 12 times 4 is 48. 32 minus 48 is a negative 16 plus 5 is negative 11. So now let's sketch a quick graph. I've got those two ordered pairs, 0, 5, and 2, negative 11. The rest of the graph follows the arrows that I have on that number line. So let's plot those ordered pairs. 0, 5, I'll put here. 2, negative 11, I'll put right there. I'll remind myself that I have 0 slope at each of those. And then I'll follow the path here that I have to go up, down, and then back up. And then we do that in a nice smooth way because we have a polynomial. So I'll just kind of draw it like this. Okay. All good. Okay, let's look at this function here. Cube root of x times 3. Do you agree that you can take the cube root of any number, positive, negative, 0? Yes? So it's a function that's defined for all values of x. But now take the derivative and go looking for the critical numbers. When you take the derivative, the 1/3 multiplies with the 3, so I just get a coefficient of 1. But then my new power is a negative 2/3. Which means that x is in the denominator. There are no values of x that make the derivative 0 because there's no factors of x in the numerator. But there is a value of x that makes my derivative undefined. X is 0, right? So f prime does not exist at x is 0. This is our only critical number because it is in the domain of the function. Now we're going to look at the sign of the derivative to help us decide whether or not that critical number is a relative maximum or minimum. Let me move that over. And I do. All right. So start with f of x is the cube root of x times 3. This derivative is x to the negative 2/3, which I can write as 1 over x to the 2/3. So I take the factor that's in the denominator, set it equal to 0, and I can kind of eyeball it and see that that's 0 when x is 0. Now we're going to check out the sign of the derivative around x is 0. Well, what kind of power is a 2/3 power? What does that mean? If you were to write it in a radical form, what would it look like as a radical? A cube root squared. A cube root squared. It's squared. No matter what number I put in there, it's going to be positive. So my derivative is always positive. That means my graph increases everywhere except at x is 0. It didn't either at x is 0. So I would say f increases for minus infinity to 0, and then again from 0 to infinity. So the graph looks like this. But how could that be a critical number? What happens there at 0? The graph gets nearly, it's not a hole, this is defined everywhere. The tangent line is vertical. So the graph itself stands nearly vertical through the origin. This when x is 0, y is 0. All right, so if I plot that point at 0, 0, my graph is nearly vertical right there. So here's the tangent line. So it's going to pass through there and then stay vertical. So it can do probably this. It's going to come up, get vertical, and then maybe go down a little bit. Because you know it's not a straight line, right? We're going to verify that it does this by using the sign of the second derivative. I drew this graph so that it kind of bends upward. Instead of this way, I drew it that way. This part of the graph is said to be concave upward. This part is concave downward. Both are increasing. I can also have a part of the graph that's decreasing and concave up, or decreasing and concave down. Concave down would kind of spill the water out. Concave up would hold it. But in a portion of the graph that's concave down, the tangent lines get smaller in size, or the sign of the derivative gets smaller. Where the graph is concave down, I'll start out with a negative number and then I'll get a bigger negative number here. So where the graph is concave down, f prime is decreasing. Where the graph is concave up, I start out with kind of flat tangent lines and then they get steeper. So f prime is increasing. Or if I have a negative number, they're big negative numbers, and then they start to get smaller in size. Well, I know that f prime tells me where f increases or decreases. So it's f double prime that's going to tell me where f prime increases or decreases. So it's on intervals in which f double prime is positive, we know that f prime is increasing. But if f prime is increasing, then the graph of f is concave up. On intervals in which f double prime is a negative number, then I know f prime is decreasing. If f prime is decreasing, then f itself is concave down. The values at x in which f prime is 0, I'm sorry, f double prime is 0, are going to be called points of inflection. They'll play the role of the critical number and help us analyze the sign of f double prime. Technically, it's not a critical number unless the an inflection point unless the concavity changes. So the values of x at which f changes concavity are called inflection points. More points of inflection, depending on how you want to put your order of your words. So visualize this. I've got a straight piece of flexible wire. And I'm going to bend that wire, say, so that it makes that graph. I start bending my wire so that this part is concave up. And now I'm going to start bending so this part is concave down. The point at which that feels that stress of changing in the bend is the inflection point. But it's where the second derivative changes sign. So we'll first find where the second derivative is 0, and then where the second derivative changes sign. So let's take another derivative of this. In our example, f double prime is negative 2/3 x to the negative 5/3. I should put that. In our example, f double prime is negative 2/3 x to the negative 5/3, which I can write as negative 2 over 3x to the 5/3. So this is going to change sign where any of the factors in here are 0. Here the denominator is 0 when x is 0. So a possible inflection point is x is 0 from here, makes the denominator. F double prime does not exist. Or where f double prime is 0 is possible inflection point. Now we're going to look at the sign of the second derivative around that inflection point. X to the 5/3 means we take a cube root of a number and then raise it to the 5th power. Those are both odd actions. So the cube root of something negative is going to stay negative. Then to the 5th power, it will still be negative. So if I put a -1 in for x, -1 to the 5/3 is negative. Multiplying it by 3, it's still negative. Then I have a -2 divided by a -3, and that's going to be a positive value for that second derivative. 1 to any power is 1. So if I put a 1 in here, I get a -2/3. So my second derivative does that, which says that my graph is concave upward here and concave downward there, the way that I've drawn it. Okay? So the concavity of the graph helps us refine what the graph is going to look like. For polynomials, it's kind of boring to find the inflection points of polynomials. But let's go back to our first example, which our graph was up, down, and back up. And let's see where this thing is concave up and down. The graph tells us it's concave down until it hits some point in here, and then it becomes concave up. So let's write down our first example again and redo it so that we include this business about inflection points. So from our first example, we had f of x was what, 4x cubed. Was this plus 12x squared or minus? I think it was minus, plus 5. And we had that our first derivative was 12x squared minus 24x. And so remember, our critical numbers were x is 0 and x is 2. And now let's take the second derivative. And I get 24x minus 24. So if we're interested in where this expression is positive or negative, then the most obvious step is to first find where it's 0. That's going to be our inflection point. So set f double prime equal to 0. And you're solving the equation 24x minus 24 is equal to 0. So x is 1. We already know what the graph is. We already know it's concave down to the left of 1 and concave up to the right of 1. But let's do the business on the number line to verify all that. Put that number here, and then tell yourself you're looking at the sine of the second derivative to help us make a decision about the concavity. So we're plugging numbers in up here that are in intervals around 1. So if I pick 0 as a representative to the left of 1, this whole thing would be 0, and I get a negative second derivative. And if I put a 2 right here, my second derivative is positive. And so my graph is, as I said, concave down there, concave up here. So if we write that as an interval, it's concave down from minus infinity to 1, and it's concave up from 1 to infinity, just as our graph showed us. Right, there's that inflection point at 1. This was at 0, what was that, 0.5, and this was to -11. And then 1 would be 9 minus 12, 9 times -3. It's concave down here, concave up there. Okay. It's not always going to be smack dab in the middle of your two critical numbers. It's just that easy polynomial. Okay, let's look at this next graph. Another polynomial. So try not to act too bored. Let's let f of x be x to the fourth minus 2x cubed. I want you to do a boatload of things in 5 minutes or less. I want you to give me the critical numbers. I want you to give me intervals in which it's increasing, decreasing. Give me the inflection points. Give me concave up, on, concave down, on, and then we'll sketch a graph. And I guess we should also identify relative max and relative min. So for the first bit, we do everything with the first derivative. We analyze its sign. First derivative is what? 4x cubed minus 6x squared. We're going to set that equal to 0 and solve for x. And so we'll just factor out, I don't know, what do you factor out? 2x squared. All right, that is 0 is equal to 2x squared times 2x minus 3. Set each factor equal to 0. 2x squared is equal to 0 when x is 0. 2x minus 3 is equal to 0. Move the 3 over, divide by 2. Do that in my head. Those are our critical numbers. Now we're going to put them on a number line in order and get the sign of f prime to tell us about the direction of f. This makes it easy to plug it in here in the factored form because this first factor is squared. So no matter what I put in there, it's negative, positive. Don't listen to what I say, listen to what I mean to say. It's an x squared, so no matter what I plug in here, it's positive. So whatever the sign of the second factor is the sign of the derivative. So if I put a -1 in there, -2 minus 3 is negative. If I put a +1 in there, 2 minus 3 is negative. If I put a 2 in there, 4 minus 3 is positive. So I have a graph that's going to go down, continue to go down, and then go back up. So I only have it increasing to the right of 3 halves. But it decreases to the left of 0. And then again from 0 to 3 halves. It doesn't do either increase or decrease at 0. So I have to write that as 2 separate intervals. So you're thinking right now your graph looks just like a parabola. But it doesn't. You're just going to have to wait until Wednesday to find out. Let's pick this example up on Wednesday. Remind me of it. And we'll do the business with the second derivative to figure out what's going on. We can already answer this part. We don't have a relative max. We do have a relative min at the critical number here. Do you want to ask something?
Would it be increasing on 3 halves to infinity?
Yeah, what did I say? 3 halves to infinity. You're right. 3 halves to infinity. Thank you. I sure hope my other classroom has some markers because those are dead, dead, dead. I got a 2-hour class next. Okay, cut this off.